in a problem set. Let's take a look as to how to do some of these problems. I'm not going to do all of them. I'm going to leave some of them for you to do. We should know that when we start problem 18, though, that we have a series of equivalents for atmospheric pressures, and that's 1 atmosphere equals 760, that's millimeters of mercury and torr. These are two the same, and then 101.3 kilopascal. Okay, we should know those. Please have those written down, like do whatever you need to do. So this is 0.85 atmospheres. We're looking to trade or change that into torr, which is very simply, we're going to use one of these. We're going to do 1 atmosphere on the bottom so that atmospheres cancel like this and like that. And then I do 760 torr like this. We've done calculations like this before, I believe, a long time ago, so it's kind of like a reintroduction to them. Times, so it's 0.850 times 760 because they're both on top of the fraction, and that equals 646 torr. Okay, that's how I do all of them. Notice I have 1, 2, 3 significant figures there. This actually should be a decimal point to show that there are 3 significant figures there. I get 3 in my, yeah, super simple. Okay, one more example, 0. Nice. What, Benson? What? 785 torr. That's the worst 785 I've ever written. And then we're going to change that to kPa. So automatically I know the 760 torr goes on the bottom, so the torr cancels with torr. There we go. And that leaves 101.3 kPa on top. I'm multiplying these two, so that's 785 times times 101.3. I multiply these two here. I get, this is a big number, 79,520.5, and I divide that then by 760 torr. And what do I get after I divide 760 torr like that? I get 104.6. I guess if we're looking at 1, 2, 3 in the beginning, I should limit to 3, so that would be 105 kPa, like that. Okay, that's how you do all of them. We're just converting in between the two pressures. So that's good stuff. Let's keep moving. 32, calculate each of the following quantities for an ideal gas. Ideal gas means PV equals nRT. If pressure is in atmospheres, then the R is 0.0821, and that is, what will that be? That'll be atmosphere liter over mole Kelvin. Okay, there we go. Good. So the volume of the gas in liters, if 1.75 moles has a pressure of 0.985 atmospheres at a temperature of -6 degrees Celsius. Okay, so this is I'm going to go through all of this stuff here. So pressure, volume, moles, R, temperature. First of all, we're looking for the volume of gas in liters. Okay, so it's always going to be in liters. We have our number of moles, 1.75 moles. My R value, if I have atmospheres, which I do, is 0.0821, and that is liters, atmospheres over mole Kelvin. And then my pressure is 0.985 atmospheres. Now here's a tricky one. This would be my temperature. My temperature is a -6. -6 means -6 degrees Celsius plus 273. So I always put it into Kelvin, and that's going to be 267 Kelvin is my temperature. So I got PV equals nRT. I simply divide. I'm looking for volume. Nice. I'm looking for volume, so I divide by pressure to get rid of pressure on that side, and I divide it by this side. So volume equals nRT divided by P, which equals 1.75 moles times 0.0821, and then all of that poop. And then temperature is 267 Kelvin, all over pressure of 0.985 atmospheres. Now, this R value is liters times atmospheres divided by mole Kelvin. So notice that my mole cancels with moles, and then there, my Kelvin cancels with Kelvin there. My atmospheres on top here cancels with atmospheres on top there, which means I'm left with liters. Okay, so what is this going to be? That's going to be 1.75 times 0.0821 times 267 divided all of that by 0.985, which equals 38.9 liters, like that. Now I started with 1, 2, 3, 1, 2, 3. The R value is, we kind of assume, and then we got 1, 2, 3. So we're going to do 3 with this, and that's good. There it is. So I'd like you to do at least B like that. We got what? B, C. What do we have for problems here? C and D. Okay. I like all of this stuff. If it says STP, which I don't think it says that, quantity of gas in mole at 54 has a pressure of blah, 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 blah. Does anything here say STD? STD. STD. STP? It does not. So we'll move on then. Okay? So you, B, C, and D, you guys should be working on those using PV equals nRT. How many gases are shipped in high pressure? Many gases are shipped in high pressure containers. Consider a steel tank whose volume is 65 liters, which contains O2 at a pressure of 1,000 or 16,500 kPa at 23 degrees Celsius. What's the mass of O2? Does the tank, okay, so there's a couple ways you can do this. I'm going to use this to solve for N, which means that I have PV over RT, okay? So I'm going to, let's just do all of this here. P equals 16,500 kPa. Now that means that my volume is 65 liters. My N is what I'm looking for. My R value is based on kPa, so that's going to be 101 point, that's not right. It's 8.3 poop. Sorry about that. 8.413. Where's my R value? R value is 8.314. There we go. 8.314 kPa times liters over mole Kelvin. Yikes. Okay. And then temperature is what? 23 degrees. So 23 degrees plus 273 equals 296 Kelvin. There. Now when I solve for N and I get this and I plug in, that's a comma, 500,000 kPa, like that. And my volume is 65 liters, like that. And I divide by the bell, 8.314, all of that stuff, and 296 Kelvin, like that. Okay? When I get the number of moles from this calculation, 16,500 times 65 divided by 8.314 divided by 296 equals. So I get then the number of moles is 435.8, and then I'm going to keep that in my calculator, because what I'm going to do then is multiply by O2, which is 32 grams per 1 mole of O2. Okay, each mole, 1 mole of oxygen equals 16 grams, and if you have 1 mole of O2, that equals twice that, which is 32 grams. There, just like that. So I'm going to multiply times 32, which equals, this is the amount of oxygen we have in mass of grams. 86. Doesn't matter, because I'm going to round off by then. I have 4, I have 1, 2, 3, 1, 2, 3, 1, 2, 3. So we're going to do 3, 1, 2, 3 like that. So I'm going to just simply go 13.9 kilograms of O2, 13.9 kilograms. The thousands of grams here, I shortened it and then switched from grams to kilograms to make it a little bit easier. So that was 40A. What volume would the gas occupy at STP? Let's go over this one so I can show you what STP is. So we're going to do this again, except this time we're going to do volume. We're not sure what the volume is. The pressure at STP is standard temperature and pressure. So that would be 1 atmosphere. I'm going to use 1 atmosphere for that. The number of moles, I go back to my number of moles, which was 345, I believe it was. Let me just find out here by dividing by 32 on my calculator. So the number of moles, there is 435.8 moles. 435.8, that's the number of moles. My temperature is going to be 273 Kelvin, and my R value at atmospheres is 0.0821 liters atmosphere over mole Kelvin, like that. Okay, so I'm just solving for V. So PV equals nRT, and V equals nRT over P, like that. And I just simply plug in 435.8 moles times 0.0821 times 273 Kelvin, and then all of that is divided by 1 atmosphere, and that will be our V. So I get 9,768 liters. I rounded up, and I probably shouldn't go 4 places. It should probably be 9,770 liters, like that. Good. Okay, I want you to finish off. Nope, we're going to stop at 48. That'll be part 2.